And we look at Chapter 4, Linear Relations. So again, in Pearson, Math Makes Sense, this book right here, it's going to be on page 150 is where we start. That's where this page is right here. And linear relations. Okay, so the question here on this very first page is, how do you think music sales have changed over the past 10 years or 20 years? In what format do you buy music that you listen to today? In what formats did your parents listen and buy the music that they had? So things have changed, obviously, in lots of areas of life, and the data surrounding changes can be expressed in something called relations. So we can relate to changing things or two variables that can change. And a lot of times we set up a mathematical relationship to describe the relationship between those, the connection between those changes. So linear relations, and we'll talk a little bit about this, but linear, the root of this word is line. So linear relations would be straight line relations, where there's a direct relationship between the change of one thing and the change of another. Okay? So that's what we're going to be exploring in this chapter, something called linear relations. And that is how two changing things relate to one another. So for example, if one of the examples we're going to talk about a lot is a job. I mean, how many of you have a job right now? Just curious. You work for some money. Okay, not very many of you. It's great. You're in grade 9, so I wouldn't expect you to have a lot of jobs. Maybe some of you babysit or work part-time at your parents' business or whatever it is. But if you think about your working experience and the money that you get paid, that money that you get paid depends upon how many hours you work, right? So there are two things that can change there. That is the number of hours you work and the amount that you get paid. And one thing stays the same usually, and that's your pay rate, right? What you get, your wage, what you get paid per hour of work or something like that. So you can see that there's a relationship between hours worked and money that you earn, okay? And that's a very typical situation that we will study in math. And we can plot points that correspond to each other. So you work this many hours, you get paid this much. You work this many hours, you get paid this much. Oh, you only work this many hours this week, you get paid this much. And so there's that relationship. They move together, right? And so we're going to explore things like that. So if you turn to your notes that you should have in front of you there, they look something like this. And if you lose your notes or can't find them, you can obviously find them on mrmathwell.com. They are or will be up there very shortly. I think they are right now. And you can download or view them at home if you forget your paper at school, or if you lose it, you can print it out again. All right, so what you will learn. Well, we talked a little bit about what linear means, what relations mean. You will learn to use expressions and equations to generalize patterns, verify a pattern by using substitution, graph and analyze linear relations, and interpolate and extrapolate to solve problems. So I will explain all of these terms and all of these things as we move through. Here are your key words, and again, on your notes package, if you would like to use this first page to sort of summarize some of the definitions that we come across, you can put them all in one spot. The middle section there, if you make any mistakes or have any difficulties, you should maybe think about jotting those down. Like I had problems with determining what the independent variable was, okay? Or just say independent variable, question mark. Something to help you remember what you need to kind of go back and focus on before the quizzes or before the exam. And then of course, you usually have on these notes a place for you to start to build your cue card. And as a matter of fact, if it lends itself to it, well, you could write everything here for your cue card, and then you could cut this out, I suppose, for the exam and use that. You would be cutting into the second page, I suppose, on this double-sided notes package. But anyways, you could straight build your cue card here and actually use this for the exam if you wish. So let's begin then. Let's begin. Section 4.1. All right, here we go. All right, so writing equations to describe patterns. So math is, and I can tell you, I teach grade 9, I teach grade 10, I teach grade 11, I teach grade 12 calculus, the advanced placement university calculus, I teach it all here. And I can tell you that recognizing patterns is probably the one most important thing that you can do in math, is to recognize patterns and to be able to determine sort of what you want to project an answer based on the pattern, or you want to describe in sort of short form what's happening there. And if you can describe it mathematically, that's the key to mathematics. So it's all about recognizing patterns and detailing or explaining those patterns mathematically. That's a huge part of that. So that's what we're going to study today. This is foundational to all your future math classes, okay? All right, let's start with some definitions, okay? A variable, what is a variable? The root of that word is what? What would you say the root of this word variable is? What's a guess? It's usually kind of the first part of the word. Vary, yes, vary, like V-A-R-Y, vary. And what does it mean to vary? If something varies, it means what? It means it can change, yeah, right? The temperature varies from day to day, as we know, here in Canada, right? It was pretty warm yesterday, and today it's minus 25, 30 something with the wind chill. Wow. So the temperature varies, it changes. Okay, so a variable is a letter, and we use letters in math. This is algebra, and just so you're not totally shocked at this, you've seen this before, but we do have letters in math that represent, okay, a letter, and we'll say representing a quantity, and that's like a value or some kind of thing, like the temperature, like I mentioned, that can change or vary. Hello? Yes, go ahead. Turn off the lights. It'll help you better back there. That can change or vary. You could also come up to the very front here. It's a lot easier to see from up there, from up here. At the very back. I'll say a letter representing a quantity that can change or vary. Now, in these linear relations and equations, lots of times we have two variables. Okay, we're not going to deal very much with three variables, but lots of times we'll have two, sometimes just one. Okay. Operations, well, obviously operations, you know what operations are. Those are the mathematical operations like adding, subtracting, multiplying, dividing. Right? Adding, subtracting, multiplying, dividing. Those are the main ones that we're going to focus on. There are other mathematical operations as well, but those are the basic ones. Okay? So you understand what a variable is, what an operation in math is. Let's talk about the difference between an expression and an equation. And we'll zoom in just a bit if I can. Well, maybe that's too much. So the difference between an expression and an equation. An expression is a mathematical, the blank there is statement. I'm going to ask you to put statement here. A mathematical statement made up of numbers and or variables connected by operations. It does not include an equal sign. Okay? So we've already talked about polynomials a little bit, right? And this is a single polynomial term. It's a monomial, and it's a multiplication of a letter and a number here. 3p is your example. Okay? So 3p is a monomial, polynomial, but it's an expression. Okay? It just shows you, it represents an amount. 3 times whatever p is. It could be whatever p is today or whatever p is at the moment. The value for p can change, and right now it's unknown. But that is an expression. An equation is very similar, but an equation is a mathematical statement where two expressions are equal. And this is the focus of what we're going to be talking about when we talk about linear relations and linear equations. So how do you find out what p is? Well, you can find out what p is if you have an equation. If you know that 3 times some unknown number equals 9, as in our example here, well, then now you can figure out what p is. So today, p is 3, or for this particular equation, p is 3. And of course, if I changed the number, 9, and said 3p equals 15, well, you would be able to tell me that p here equals what? It equals 5. Very good. Yeah. So you know a little bit about this. You've done this in math before, equations, solving for variables. We're going to expand on that a little bit. You're going to solve for unknown variables using the operations. Okay? All right. So let's take a look at example number 1 here. It says that Luke wants to earn money this winter shoveling driveways. He will get paid $9 an hour. All right. So we opened up this lesson by talking about one of the most popular kinds of relations that we can think of, and that is time spent working and money earned, right? So that is very popular, very common. You guys will be very interested in that as you kind of grow and like realize, hey, I need money for things. I want to get some money. How do I get money? Well, you got to work for it, okay? And that's the best way to get money. You don't want to steal it. You don't want to like draw it and make it and cut it out and try and pass that off for a phone. It's like, oh, it's $1,000. Look at it. I put my name right on there. You can't make money. You can't steal money. You have to earn money. Okay. So the two quantities that are being compared in this particular problem, what are they? What's one of them? I just mentioned the two of them in my examples. One quantity in this situation is, anybody? Be brave. There's time worked and money earned, okay? So time worked and money earned. That's what connects, those are the two things that connect to determine how much you're gonna get out of the situation. Okay, so the two quantities that we are comparing in this problem is time spent working, and that's going to be in hours, right? Why do I know it's going to be in hours? Yeah, look at right here. The wage, or this connection piece, it says $9 an hour. So right there, you kind of see what the two quantities are, or at least the symbols for the two quantities. So we have hours, time working, and we have the money earned, okay? Money earned. And that's going to be in dollars. That's our unit. Okay, so this is the rate here. This is a rate, and that's going to be important for you guys to know. Your hourly wage or your rate. So hours worked, let's make that equal to a variable h. And let's make money earned equal to the letter capital A for amount earned, okay? So for our examples, that's what we're going to start with there. All right, here's an interesting question, and this is actually, as I mentioned earlier on in the lesson, that this is one of the things that you might have trouble with. I don't know. In certain examples, this is difficult to determine which variable is the independent variable, which variable is the dependent variable. Because we have two variables here, and one is called the independent variable. So first of all, what is an independent variable? Well, think about the name independent. If you're an independent person, you stand strong and you stand alone, and nothing can affect you. You're very independent. I can do this on my own. I'm going to do what I'm going to do, right? Think about that kind of independent, right? So a variable that's independent would be a variable that stands alone, unaffected by the other variables you're measuring. And that's what is part of what our definition is going to be. So let's jot that down here. And I'll type this so it's a little bit easier for you guys to read. Okay? So this independent variable is a variable that stands alone, not affected by other variables that you measure. So it's the one that you, another way I like to think about it, it's the one that you start with, okay? You start with this changing quantity, and then you go ahead and you measure the second one. So which one do you start with, right? And in the dollars earned and in the hours worked, you always start with, okay, how many hours did I work? That is going to indicate how much money I earn, right? Okay? So it is the variable that stands alone, not affected by the other variables you measure. Also, I mean, the word independent means that it is not dependent on another changing variable. Okay, in the question. So that's another way to think about it. It's not dependent. And when you define things, you shouldn't use you shouldn't use the term in the definition. So that's why I kind of started with this other sentence. But really thinking about this being not dependent is very helpful. It is super helpful. Okay, I'm going to make that a little bit smaller now. Okay, a variable that stands alone, not affected by other variables you measure. It is not dependent on another changing variable. Now, a dependent variable, okay? The variable that is determined by the other variable. So it is determined, or it depends upon the value of the other variable. And this is when, of course, we're talking about, two variables, just one or the other, independent, dependent. So the variable that's determined by the other variable, it depends upon the value of the other variable. So if you're thinking about the time worked and money earned, you don't say, okay, how much money is involved today, and then I have to work backwards to find out how much time I have to work. That seems a bit awkward, right? I mean, you could figure out, if you're getting paid $9 an hour and you make $27 that day, you could figure out, okay, $27, I'm starting with that money, and I can work back to how many hours did I work, right? 3, okay? But that the nature of the variables says in that situation that you start with the number of hours you work, and then you calculate the money earned. So what do you start with, and what do you calculate? And so the dependent one is what depends upon the other one, okay? Does that make sense? That kind of makes sense? That's why it's difficult, because it's kind of like, well, they're connected. If you have one, you can find the other. Yes. But you always kind of start with one, and that depends. Now, in other situations, let me give you a hint. In most situations, time is the independent variable, okay? Think about it. How much snowfall do you get throughout the year? Well, snowfall is clearly what you measure, and that depends upon the time of the year. So as time goes by, we can't really stop time, we can't really slow down time or back up time. Time just keeps marching on. It's the independent one. Got it? Time. You can't touch me. So time is independent, and then we measure things, right? How far away from the school are you if you've walked for 5 hours? Well, 5 hours would be, right, the time, that's the time that's gone by, and then you measure how far away you are, okay? The only cases where time is the dependent variable would be if you are measuring a time in a race or something, right? Okay, so now I've got 100 meters here, and when I say go, I'm going to start the time. Go. Run, 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 run. Stop. Okay? What did I measure? I measured time. So time would be the dependent variable. That's what I measured. What did I start with? I started with the distance. So in that case, distance is what you start with. You got to do 100 meters, so you calculate the time it takes you to get there. And, conceivably, your rate would be sort of that constant rate. Now, I know you're starting from 0, and you're ending up at whatever speed you're at, so it does change throughout, but there would be an average rate. So if you think about this, in a graph, you running a race would not be a straight line graph. It would be a graph that kind of goes like this, and then it kind of curves up like that, right? Because you're starting off, you're very slow, like you haven't covered a lot of ground in the first second, but then in the 10th second, you're covering a lot of space because your speed is increased. So again, I'm getting ahead of myself here, but in a straight line, your rate of change every second or whatever would be the same. In a curved line, your rate of change changes. But I don't want to get too far ahead of myself. I think you guys can understand that, so that's why I say it. But, that's not what I want to move. All right, so let's keep going. Any questions, though, about this independent dependent variable? Because it's crucial. It's crucial. Well, that's a good start, I think. But was there a hand up? No? Any questions? All right. All right, when we're trying to figure out the quantity, what quantity is the independent variable and which is the dependent, complete the following sentence. Amount earned depends upon hours worked, and that would be your hint. So amount, I'm just going to represent that by A, okay? Amount earned depends upon hours worked. Amount earned, I'll just put it in brackets here, and hours worked, okay? And I think I've done a fairly comprehensive job of explaining that to you, so I don't think I'll beat that horse here too much more. Oh, that sounded really bad, didn't it? Beat the horse. I don't beat horses, I like horses. There's an old expression, like beating a dead horse. It's kind of like, come on, let's go, let's work. And the horse is dead. It's like no sense beating it anymore because it's dead. That's really terrible now that I actually verbalize that. That's the worst expression ever. This is beating a dead horse. You ever heard that though? Yeah. Come on, your parents or grandparents have probably said that, right? No sense beating a dead horse there. Like, oh, that's gross. Why would we do that? Anyways. Yeah, I'll probably come up with a lot of those expressions, that from my childhood that actually really are kind of bad. But that's the way it goes. Okay. All right, so let's complete this table of values. Now, how many of you remember a table of values in grade 8 or 7? Okay, so here's where you find matching pairs for your relation, right? You have two variables, you have two columns. One variable is the independent variable. That's the one you start with. And oh my goodness, look at this. We start with number of hours worked. Independent variable. See that? And it's usually on the left column. And if you remember, now I might be jumping ahead of myself a little bit too, but remember this is like the X column and this is the Y column when you do a table of values. So we'll get to that a little bit later, but on a graph you'll be able to spot where the independent variable is and where the dependent variable is too on the graph. Okay, so number of hours worked. Okay, so if I work, or if you work, let's say this is you, okay? So in this example, you're working 1 hour, and here's the rate at which you're earning money. So 1 hour, how much are you going to earn there? Yeah, $9. Now, let's do it this way. Let's say I'm going to put in brackets $sign here. Then I don't have to put dollars for my numbers here, okay? If there's a symbol for a unit, you should put it in your charts, either with every number or at the top like this to represent that that's the unit that goes with all these numbers, okay? Hours, there's no real symbol that goes with hours, right, other than just H. So hours are just hours. They're just numbers. There's no unit. Dollars can have dollars, American dollars, US dollars, euros, pounds, right? So we have to put the symbol of what we're talking about there. Okay, 2 hours is going to be 18, very good. 3 hours is going to be 27, good. And we're just multiplying these numbers by 9, right? 36 and 45. Awesome. Okay. All right. So a 4-hour shift is pretty common. If you work, now, again, a lot of you won't be working this year. Some of you might work next year. Many of you might work in grade 11 or 12. But sometimes on school days, I would caution working too much during the week. But sometimes on school days, I know of students that work, from 4 to 8. Okay, so right after school, they're working from 4 to 8. That's a common shift, 4-hour shift. So you might make, $36. I think minimum wage is way more than $9, of course. This is just an example. But minimum wage, what is it, $12, $11, $12? Does anyone know? I don't even know. 12 something? Okay. 11 something, 12 something. So, I mean, you can figure that out, right? So if you had a minimum wage job, 4 times 12, $48, okay? So you could conceivably make $48. You probably won't make enough that you'll have to pay taxes on that. So it's pretty much straight yours. There might be some other deductions from your job or whatever. But 4-hour shift might make you $50, okay? All right, so write an expression to represent the amount Luke earns per hour. Okay, so here's where we're going to write an expression, and then we're going to write an equation. So the amount Luke earns per hour. Okay, so you're going to do $9 is what he makes per hour. So this is the expression. The expression to represent what Luke earns. I'm actually going to, I don't know if I should cross this out actually. I tentatively I'm going to cross that out because per hour would just be 9, okay? But I want to get to 9h here. So per hour is $9. That's it, 9. Now if we want to include h in that expression, which I want to, we're going to write an expression for how much Luke earns. So it's going to be 9 times h, the number of hours that he works. Everybody got that? So per hour is just 9. The amount he earns as an expression would be 9 times h. Got it? All right. So that's an expression. There's no equal sign or anything. Write an equation now to represent the amount Luke will earn. So earn is A equals. So the amount he earns equals 9h. This is now an equation because it's got an equal sign in there. An expression has no equal sign. So the amount he earns would be 9h for an expression. An equation would say, hey, what is 9h? Oh yeah, that's the total amount that he earns. Okay? And again, equation has an equal sign. Just remember that. Also, please notice that the two variables that we're talking about in the question are in the equation. The two variables are right there. So in an equation, we have both variables represented. Okay? Questions? Okay. All right, very good. I like it. I like where we're at here so far. It seems like you guys are paying attention. You're doing well. So this page here says, to be careful. Oh, that's pretty small there. Okay. All right. This page says here, whenever the blank variable increases by 1. So which one is increasing by 1 here? Which side? This side's increasing by 1, right? And what variable is that? That's the h, or the independent variable. So let's put independent here. Put that in blue here. Independent. E's all over the place in independent, in case you're one of those people that don't memorize very well or don't understand. There's no ANT in independent. It's all E's, which is a little bit strange, I think. So a lot of things they have ANT at the end, right? But independent, it's dent, not ant, independent. Also for dependent, it's DENT, okay? So as the independent variable increases by 1, you can use the following strategy to find the equation. Okay. So if this goes up by 1, you see, plus 1, plus 1, plus 1, and so on, then whatever this is increased by, and each one goes up by 9, plus 9, plus 9, plus 9 each time, then you can figure out what the equation is. And these are related, okay? A and H are related by, this is 9 divided by 1. So it's just, that's where the 9 goes. So if this goes up by 9 each time and this goes up by 1 each time, then you've got 9 as the number that connects the two. Okay? And we'll do more work on this because it's like, wait, what happened there? As this goes up by 9 and this goes up by 1, the number in the middle here is actually 9 over 1. So if this goes up by 1, you just look at, that's what this example is saying. You look at how much this increases by, and that's the number that you put multiplied by the h. Okay? So you ask yourself here, does 1 times 9 equal 9? Yep. Does 2 times 9 equal 18? Yep. 3 times 9, 27, and so on. Therefore, whatever the h is, you plug the h in here, right? Let's say it's 4 now. So 9 times 4, that should equal 36. Well, for 4, we have a partner value of 36. So you can test your equation with the table of values there to make sure that whichever one is the independent variable, that's the one you put into the equation there, and then you do some calculations. What was that? And you can test your equation. Okay, so we'll do more work with figuring out equations from graphs. We'll do more work later on that. Okay, use the equation to determine how much Luke will make shoveling 11 hours in 1 week. Okay, so 11 hours in 1 week. So 11 is h. h equals 11, right? And we're to use the equation to determine how much he will make. Well, that's a. So a, we don't know. And this is going to be very important for you as you move through math, like I'm doing here. Please write down what you're given in the question and what variable it represents. So h equals 11. Important to write that down. A equals question mark. This is what I do, okay? So in my classes, I do this a lot to show what my unknown is. My givens, I say h is 11, that's given. If there's anything else, put that down in the equation, whatever. A is unknown, so I usually do a equals h. And if you are with me from now until AP Calculus, you will see me do this every time, okay? A equals question mark. I don't know. Did I say a equals h? A equals question mark. I might have said h. A equals question mark. Okay, so what we want to do is we want to use our equation, a equals 9h. So we've got our knowns, our givens, our unknowns, and then our formula. Okay, and you can think about this too, guffs. I'm not sure if some of the other teachers in the school have taught you about guffs. It's a good one to remember, guffs. Write down your givens right here, givens. Write down your unknowns, or your unknown. Usually there's just one. And then F is formula. And then S would be your solution, or now it's time to solve. Okay? So guffs, given, what's given? What's unknown? What's your formula that connects those two things? Or what's the formula that connects those things? Maybe there's more than two. And then go ahead and solve. So a equals 9h, that's the third part. And I'm only going to circle my answer, so I'm going to erase those circles. But I'm now going to input my given into the equation. So guess what? H equals 11. So I'm going to go ahead and put 11 in there. And now a equals 9 times 11, or 99. So a equals 99. In a question like this, what you should always do is you should finish with a sentence that has proper units. Okay, a sentence that has proper units. So this is not good enough. Okay, this is not good enough. You should say something like, Luke earns 99, and then please put the unit there. Okay, and then circle that. So you want to show your work this way, and then identify your answer clearly like this. So sorry, what was the question? If you put the unit after, you need to put the unit in the proper spot. For money, for dollars, you have to put the unit in front. Yeah, in other parts of the world, you might get away with that, but dollars go in front of our numbers here in this part of the world. So that's what we do. Cents is different though. Okay, cents, you put the little cents sign. So $99 would be 9,900 cents. And you actually put cents behind for some reason. But $99, you would put the dollar sign in front. Okay? I'm sorry?
What if you have dollars and cents?
If you had dollars and cents, you'd go $99 and let's say it was 12 cents. So you just put 0.12. That's how we do money. Yeah. Okay? Because 0.12 of a dollar would be 12 cents. So 0.12 of a dollar is so this is all in dollars. But that would include the cents in this part right here. Okay, good questions? Any other questions? Those are great clarifying questions. Thanks for asking those. Because I don't know what you're thinking. As good as I am, I just can't read your thoughts quite yet. I can't even read my wife's mind, and I've been married to her for decades. So I'm not going to be able to read yours, that's for sure. All right, G, let's do G. Use the equation to determine how many hours Luke will need to shovel in order to earn 72. So here we go. You can answer all sorts of questions with this. You don't always have to solve for the dependent variable. You can now use the equation to solve for any unknown, any variable part. So what am I given? I'm given A equals 72. Awesome. I don't know how many hours that's going to take to get there. But because this is such a simple equation and you guys are so lightning fast with your single digit multiplication and division, you know what the answer is right now. But let's show our work and let's do this. I know this doesn't seem maybe necessary. You're like, oh, this is too easy. I don't have to show my work. Please practice showing your work because I'm sorry, but I will hammer you if you do not show your work in grade 12 and you will get everything wrong. Okay? You can't do stuff in your head in grade 12. So learn now. Practice now so it becomes second nature to you. So I've got my given, got my unknown formula, A equals 9H, wonderful. Where does 72 go here? On the which side, which variable? I know, too easy. 72, right, equals 9H. So to get H by itself, because that's what we want to do when we solve an equation, we want to isolate for the unknown variable. In question F here, the unknown variable was already isolated all by itself, so we didn't really have to do any operations to isolate it. But here, H is on this side. Okay, so to get H by itself, this is where the operations come in, and you're going to need to do opposite operations. So 9 is multiplied by H. In order to get rid of the 9, I have to do the opposite operation and divide by 9. And in an equation, what you do to one side, you always have to do to the other side. It's kind of like a balancing act. Okay, you've got an equation, they're equal. Everything is balanced on both sides. If I divide this side by 9, guess what? It goes down. And so we're not equal. It's not an equation anymore unless I divide the other side by 9 too. Then it's equal again. So whatever you do to one side as far as operations go, you have to do to the other side as well. And if you keep that in mind like it's a balancing act, then that's easy. So 9 divided by 9 is 1. So now I have my H all by itself. I'll just kind of go over here. H is all by itself. And what's on the other side? This simplifies to 8. Okay, so H equals 8. I use my mind to understand the answer of the problem is connected to h equals 8 somehow, and I would then say, Luke needs to work 8 what? Hours. Yep. And I would circle that answer. I've got all my work shown. I've got my givens, my unknowns, my formula, my solving process. Okay, and I get it. I was in grade 9 too, and you know what? This kind of stuff came pretty naturally to me, as you can probably understand. I knew what this answer was. I'm like, seriously, I'm gonna show all my work? That was me too. I get it. But now I understand why it's important. So please practice this. It'll literally take you 22 seconds more than just writing down the answer sentence. I would guarantee. Okay, any questions though about that page? No? Okay, let's keep rolling. We got a bit to cover. We'll probably take it right to the end of this period with all this instruction. So, all right, so this next page here, now we start to get into some word problems, and this is where you really have to start thinking about it. But you've got all the basics here that you need in order to solve these problems now. So this question talks about a banquet hall. A banquet hall has give me a second. Try and zoom in appropriately here. View. Okay, let's see if I can do this. 110. Oh, that's good. Just a little bit bigger for you at the back. Okay, so a banquet hall has small square tables that seat one person on each side. The tables can be pushed together to form longer tables as shown below. And you guys have probably experienced this, right? Your family walks into a restaurant, all there is like this one table that can sit 4 people. Well, your family happens to be 6 people. That's my family. So I walk in there, and what do? Well, it looks like all we need to do is push one more little table beside the other one, and then 6 of us can go around that. And that's what this says. We can put 4 people around one table. You can put 6 people, 2, 4, 6 people around 2 tables. How many do we put around 3? 8. Okay, so the first part says sketch the next 2 table arrangements in the pattern. So there's a pattern. Let's sketch the next 2 table arrangements. I'm going to have, this doesn't have to take long, doesn't have to be real neat. But we're going to have 4 tables now, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then, of course, you guessed it, we're going to go with 5 tables next. We're going to have and then we're going to have 12, right? So 1 table, 4. 2 tables, 6. 3 tables, 8. 4 tables, 10. And 5 tables, 12. Okay, so we're getting somewhere there now. We're getting somewhere. We know how 2 quantities are connected. And what are the 2 quantities? What's one of the quantities we're talking about in this question? Just name it. Shout it out. People and tables. Yes. Okay, so tables and people. Okay, what do you think? What do you think would be the independent variable of those 2? Tables. Notice how we start with the table and put people around it. Now let's add a table and put people around it. Let's now, what are we going to do? Add a table. So our independent variable would be table. Very good. And I may be jumping ahead. I think I am. I'm sorry. All right. Sketch the 2 table arrangements. Got it. What stays the same in each table arrangement? What stays the same in each table arrangement? Oh, this is interesting. In each of these pictures, and maybe it's easier to look at the pictures of the actual people. So what stays the same? Well, if you think about it this way, this person and this person on the ends, they actually stay the same. You see that? They stay the same. Here and here, here and here. Each time we add a table, we add a pair of people in the middle. 3rd table, we're adding now these people. Okay? So it could be said that maybe these 4 people stay the same, right? Like it looks like actually they stay the same. So we could say these people as well, this one and this one, because they stay the same in each picture. Look at that. So we've got the original 4 people stay the same. So what stays the same? We'll just say that original 4 people. Okay, again, this is going to help us build the equation. This is going to help you maybe understand things a bit here. So the original 4 people. So what changes? Well, tables change. Table numbers. And 2 more people each time. Okay. So we've got some numbers here. Original 4, 2 people are added each time. Let's talk about the variables again. So we talked about that already. So the number of people depends upon number of tables. Okay. So if we're given one of those, we could probably solve for the other one. So there's an equation that's starting to emerge, right? So these two will be equal somehow. So the independent variable, and I'll just go like this. Independent variable is number of tables. Or let's make that t. Okay, so the independent variable is number of tables, or t. The dependent variable is going to be the number of people. Or let's just make that p, I guess. And lowercase p, doesn't matter. Doesn't really matter. Okay, was there confusion over there? Can I clarify anything? You got it?
Yeah.
Okay, good. All right. We're getting real close here. We're getting real close. Now, if we go back to the table of values, I honestly think that's going to be probably the most important thing we can look at, the table of values. So let's complete the table of values here now. So if we have the number of tables, if that was 1, how many people were around one table? 4. Okay. So we had 2 tables, then we went to 6, which makes sense because the original 4 people stayed the same and we added 2 people. Awesome, so that's 6. 3 tables. We had the original 4, and then we've added now 2 groups of 2 people. So that's going to be 8. 4 tables. We have the original 4 people plus now 3 groups of 2 equals 10. And 5 tables. 4 groups plus 4 plus 4 groups of 2. So we have 12. Okay. So now here we go. Now we have to write an equation that relates the two. All right. Okay. So I'm going to have tables. That doesn't really matter which side you write things on. I guess so far we've been writing the dependent variable on the left side. So people is the dependent variable and our independent variables on the right side. I think that's probably wise to do. You don't have to do it that way exactly every time, but I think that's a good idea. So let's put our dependent variable on the left and then our independent, or the input variable, on the right. So should I just do this? Am I done now? Is that good? 4 times the number of table. Well, that works for this one. 4t is 4. 4t, 4 times 2 is 8. That doesn't work. Okay, all right. Well, I guess 4 doesn't work. Let's take a look at the actual table of values and let's see if we can figure something out here. We've got, plus 1, plus 1, plus 1, plus 1. Okay. And what's going up here? This is plus 2. Oh, plus 2. Okay, so each one is plus 2. So what did we say earlier about this situation when we have the same number being added and this is plus 1 each time? This is the number here. Number 2 is what goes here. Didn't we do that before? Okay, all right. And that's correct. So am I done now? The number of people is 2 times the number of tables. Well, let's see. 2 times 1 is, I'm a little bit off. What's the solution there? How can we fix this? Sorry? What'd you say? Okay, plus 4. Okay, let's see. Plus 4. 2 times 1 is 2 plus 4, it would be 6. Oh, shoot, I need 4 here, not 6. So you're on the right track. Okay, let's try plus 2. Let's try plus 2. Well, 1 times 2, so 2 times 1 plus 2, does that equal 4? Oh, it does. What about this one? 2 times 2 plus 2, that's 4 times plus 2. 2 times 3 plus 2. Okay, is 6. Oh, nice. So you can actually see that there's 4 is 2 plus 2. So 2 plus 2 groups of 2. That works. 2 plus 3 groups of 2 works. 2 plus 4 groups of 2 works. And 2 plus 5 groups of 2 works. So this is the equation. Now that takes a little bit of thinking. It takes a little bit of trial and error. I get it. But that's sort of how you're going to start to connect and build an equation. Okay? So we just ramped up the difficulty there for this example quite a bit from the first one. But I hope that you're kind of understanding that. And it shouldn't take you long to connect those two variables and to find out, okay, what is this multiplier? And that's going to come from this number divided by whatever this goes up by. Whatever, so this was plus 1, remember? 2 divided by 1. And then you might have to add or subtract something on top of that. Okay. That's the equation. What is the expression that can be used to represent the number of people? Okay, so really, we just don't write this as an equation. The expression for people is 2t plus 2. Okay, that's the expression. It's not an equation. All right, so take a moment, and I want you to answer these next 3 little pieces of questions. So, for example, use the equation that we just did, that we just figured out, to find out the number of people at 6 tables, and then at 10, and then at 25. So please go ahead and show the equation, plug in the values in the value in the appropriate spot, and then find an answer. Okay? You don't have to do a word answer for each one of these. Just kind of circle your answer at the end there, please. Okay? So take a few moments and do this. So find out how many people. And again, I'll write this one up here for you, 2t plus 2. That's your equation. So where does 6 go in this equation? And then solve for the number of people. Okay, that's what we don't know. Okay, go ahead and do that. All right, so this is what 1, 2, and 3, Roman numeral 1, 2, and 3 should look like. What we do is we put the number of tables into the equation in the appropriate spot. So t equals table, so I'm going to put 6 in for t in that first one. Then I'm going to multiply 2 times 6 is 12 plus 2. 12 plus 2 is 14. So the number of people that could sit at 6 tables in this situation is 14. You do the same thing for the next 2. We use our equation, putting 10 in for t. In the second one, we get 22. And we put 25 in for t. In the third one, we get 52. Don't go anywhere yet. The bell is for me, not for you. We have one more question to do, and then I'm going to give you your homework. Okay, so keep your pencil out. What number of tables are needed to seat 30 people? Last question before we go. Okay, so people is 2 times t plus 2. So I need to find out how many tables are necessary for 30 people. So I put 30 in for p, and we have to solve for t. How we do that? Subtract 2 from both sides. I'm going to have 28 equals 2t. The next thing I'm going to do is I'm going to divide both sides by 2. Shh, quiet please. And I get 14 equals t. So the number of tables needed for 30 people would be 14 tables. Okay, your assignment for tonight, I'm going to give you part of the assignment from 4.1 because you can do half of it. So it's going to be 3 to 9. That's your assignment for day 1 of this 4.1 lesson. Please write all that down. Make sure you have that down, then you may be dismissed. See ya.